This is Steve Caravella. He's a solutions architect at Siemens Digital Industry Software, working with the Capital Software product line. He's got several decades of industry experience in engineering and manufacturing support roles at major aircraft OEMs, working on a variety of aircraft models in production and service settings. Steve's been involved in the movement towards model-based design since the early days and was a key member of the team that developed and received the first FAA approval for the implementation of the model-based design approach in the early 2000s. And so Steve's going to be talking about ways today to increase manufacturing profitability through the use of models of the electrical system design. And again, if we will have a little bit of time for questions at the end, hopefully, if you put them in the chat now or while he's talking, then we'll get to them afterwards. Take it away, Steve.
Okay, thank you, David. Hello, everyone. Today we're going to look at some of the pressures in the aerospace industry surrounding EWIS, or otherwise known as the Electrical Wiring Interconnect System. And specifically, we're going to look at how to exploit an electrical system model and how it can help us achieve greater responsiveness, improve quality, and higher profitability in manufacturing. A little bit about myself. As David had mentioned, I work for Siemens as a solution architect in the Integrated Electrical Systems software segment. My mission here is to serve the A&D industry by helping companies understand the benefits of using advanced software tools and automation to meet today's needs, as well as championing the development of capabilities needed by the industry in our Capital software product line. I joined Siemens earlier this year, having spent 28 years in the aerospace industry at several aircraft manufacturers. I've had roles in engineering, certification, and manufacturing support, working in different parts of the business ranging from customer service and modification to new product development. In the process, I've had the privilege of working with airline customers, suppliers, government agencies, and US and European regulatory agencies. So let's start the discussion today by looking at what some of the challenges the industry is facing. Whether you're manufacturing electrical harnesses as an OEM or as a supplier, your team is likely under more stress than ever. There are business and market constraints present on all sides. It begins with increased harness complexity driven by more electric platforms and the need to rapidly transition new designs into production. Customers expect ever lower cost assemblies delivered just in time, while at the same time threatening to vertically integrate harness manufacturing. At the same time, platform designers are continuously changing their electrical systems in response to business and market needs. So consequently, this drive changes on a more frequent basis in response to changing demands of customers. Everyone expects harness suppliers to keep up, transitioning these changes into production quickly and with a minimum of cost and schedule impact. Add to this the challenges of the competitive landscape and loss of experience and tribal knowledge, and it results in a big squeeze. Overall, these trends make it more difficult for harness manufacturers to meet expectations for responsiveness, quality, delivery time, and profitability. So we start by recognizing the need for aircraft differentiation is driving the need to increase electrification. There are more demanding missions requiring new capabilities while achieving higher reliability and lower aircraft weight. This has led to a vast increase in the number and extent of electrical systems on these aircraft. We can see just how much by examining the amount of power generation on a modern aircraft. This has had consequent impact on the complexity of the aircraft distribution systems. Today, it's not unusual for a modern aircraft to have electrical systems with more than 500 kilometers of total cable length, with up to 100,000 wires and more than 40,000 connectors. This now puts the electrical system front and center in implementation of new capabilities, and there's a lot more at stake with getting it right. A problem discovered in first article integration or transition to production can have a major effect on the development cycle, potentially costing billions of unexpected dollars. This not only puts a program at risk, its cost and schedule, but also the reputations of the program team, the reputations of the business unit team, and in the worst case, the viability of the company itself. So at the same time, the market is expecting platform OEMs to implement more variants than ever before. They not only must answer these demands from their customers, but they're also using responsiveness as a way to differentiate themselves and gain competitive advantage. Regulatory certification is becoming more and more stringent. Not only are they changing in response to new incidences, but the ability to avoid their application through grandfathering of new aircraft derivatives has all but disappeared. Finally, OEMs and suppliers must implement changes arising from design improvements for cost reduction, manufacturability, reliability, and performance. Together, these vectors of change stress harness manufacturers, whether they are vertically integrated within an OEM or at an external supplier. Suppliers need to respond to change from both the OEMs and their own harness product and process engineering teams, and they must do this urgently as changes are frequently communicated at the last minute with little time to spare if production deliveries are to be met. All this results in a new manufacturing reality, more harness variants produced in more frequent production and in smaller quantities. So let's start by looking at the challenges that can be encountered during production ramp-up. I'm going to give you a representative example here. We know that there's a ramp-up period at the start of production and may typically plan for a smooth ramp-up focused on reaching, say, 80% efficiency by the time we start full-rate production. However, the reality can fall short due to unplanned issues. Perhaps there are unexpected design changes or mistakes in creating tooling, work instructions, or errors in other production process support artifacts. We respond to that with rework, expediting, or overtime, resulting in unexpected scrap, fees, and labor costs. Suddenly, at the time we expected to start full-rate production, we're only, say, at 60% operating efficiency. While this may not sound that bad, the problem is that until we reach our 80% target some weeks later, we will be losing money on every harness. By the time we get there, it's quite possible that we have lost more money than our entire predicted profit run. So this is actually a disaster. For very large programs, the loss can be in the millions. So you have to ask yourself, why does this happen? Well, first of all, manufacturing ramp-up is difficult to begin with. And in large part, we are encumbered by outdated tools and methods. First, disconnected systems drive the need to manually transfer data. Second, existing tools were not designed to handle the expanded scope and complexity of today's demands for electrical systems. And finally, increased complexity makes it difficult to achieve first-time quality with existing approaches. This all can result in expensive discovery and iteration at critical phases of the manufacturing ramp-up. The result, missed delivery, lost profitability, and damaged reputations. So now that I've talked a little bit about the problems, the good news is that there's a transformation underway. The most sophisticated members of the manufacturing community recognize the need to change. Using a technique termed digitalization, they are applying digital technology to transform their business process. As shown here, leaders of the U.S. Department of Defense endorsed this shift to a digitally connected design and manufacturing ecosystem. Part of the U.S. DoD engineering strategy is to develop, integrate, and use models as the authoritative source of truth, to incorporate technology innovation, to establish infrastructure and environments, and to transform culture. They are already adopting model-based development techniques from concept development through design and into manufacturing to reduce cost and schedule risk, accelerate production ramp, and improve productivity. So what does this look like as we talk about electrical systems development? Key to this approach is the creation of a digital twin of the product, the production line, and product utilization. Connecting these together so that information can be accessed directly or transferred digitally creates a digital thread supporting information flow up and down the value chain. What does this enable? It enables integrating disciplines, teams, and domains for seamless data sharing and reduced delay during handover, early and frequent analysis to reduce risk by validating systems prior to and during implementation, optimization of design, production, and product utilization using simulation, and requirements traceability. However, specific to manufacturability, it supports generation of an accurate engineering bill of material, performing cost analysis based on bill of process, and improved assembly production line planning and flow. At Siemens, when we look at the EE systems landscape from a high level, it can be organized into three primary interconnected domains. You have systems and architecture definition and design, software and network design and development, and electrical and harness design and production. These are fed by upstream requirements and systems models and interact with the flows associated with electronics development. Each of these primary domains contains specific interrelated domains. Using data automation and integration along a digital thread, we are able to continuously verify and validate alignment across the domains, especially when it comes to the iterative nature of product development process and handling of change. Of course, EE Systems is only one aspect of a product's design, and the tools and product data fully exist within a broader ecosystem of enterprise-level tools and processes. Today, we are specifically discussing the manufacturing activities happening with what we describe as the harness engineering domain. So let's look at a manufacturing flow based on this approach. Having the digital twin of the product connected to production allows for an interconnected flow spanning harness design and costing, product engineering, form board design, subassembly design, process design and optimization, and manufacturing documentation. With the information in a digital form, a high degree of automation that requires no manual data reentry can be brought to bear to make this flow seamless, and the information within remains interconnected and traceable each step along the way. As a result, speed and accuracy of the flow is increased, enabling a higher level of responsiveness and efficiency. So let's take a quick walk through this flow with a 2-minute video I have. We start with design engineering, where the design of the harness is completed. This is digitally validated against system logical design for accuracy. When needed to create a variation of an existing design, it is easy to reuse existing data instead of starting from scratch. This reduces the time to complete the design and the likelihood for error. With the harness design complete, the product engineering team reviews the design to create manufacturing plans and supporting materials so that the right information is available at the right time during the manufacturing process. Next, we move to the form board design. The use of standardized libraries and rule sets reduces work and streamlines and validates the creation of the form board. When faced with large assemblies, the tools provide the capability to divide the harness into smaller subassemblies to facilitate buildup and handling before bringing together the final product. A high degree of automation can be leveraged to reduce errors and speed up the completion of the form board design. Bill of process preparation and costing is made easier using the embedded process and cost information. By utilizing process models and simulation, resource loading and cost analysis can be performed quickly and easily for different product configurations and manufacturing approaches. By capturing and using internal know-how, risk and cost can be reduced. Line balancing simulation is supported to evenly distribute work tasks across various stations and prevent bottlenecks and unnecessary idle time in the manufacturing flow. Finally, work instructions can be generated using existing data when available to accelerate their creation and minimize errors. The result is increased efficiency and increased profit margins along with it. Using these approaches, customers have reported up to 50% reduction in design errors, 30% cycle time reduction from quote to production, and 85% time reduction in form board design. Oops. So let's take a little closer look at the generation of the bill of process. So we start with company know-how, which is in the center. These are the rules and embedded IP, tribal knowledge, and constraints that are captured in asset databases and algorithms. Second, we have harness models coming from engineering, which are validated utilizing embedded rules and a high degree of automation. And third, we have the production process models, which are defined and captured for consistent reuse. From here, the bill of process is automatically generated using the selected factory and harness models, resulting in outputs that support the various downstream customers. Issues and errors and improvement proposals are then fed back into product and manufacturing engineering to continuously improve manufacturing outputs, promoting efficient product manufacturing. The integration of the tools and data enables a high level of automation to be used in this process, supporting timely and accurate updates. So I've got two examples for you. First is the merging of form boards. So when you think about it, each harness gets laid out on a form board, and when you start to look at trying to optimize factory space and available resources, you may want to build different but very similar harnesses on the same form board. So here we see two form boards for harnesses that are similar but have different branches and terminations. Typically, this would mean generating two different form boards that need to be managed. But what if we could merge these into a single multi-use tool? The answer is we can. By using a form board design tool overlay, we can identify which areas are common or different between the two harnesses, so either could be fabricated on this board. As you can see, the differences are highlighted in yellow and blue. As a result, in addition to reducing tooling costs and storage needs, the overall utilization of the tool is increased. Second thing I would like to show you is how today's tools can help with ergonomic design and efficiency. I have another short video which shows how this can be done. The design starts with the harness being brought into the form board design tool. Starting with the main backbone of the harness, it is arranged on the form board to the desired layout. Ergonomic zones are highlighted as green for the most optimum to red for the least optimum, with yellow in between. Using these colors as guidelines is easy to adjust the overall layout to improve ergonomic placement. Note that as the harness is moved and adjusted by dragging and dropping various grip points, important characteristics of the harness such as length and bend radius are automatically maintained by the tool. As we work through the harness, each branch can be arranged relatively easy into an ergonomic and efficient form board design. Okay, so having looked at what we could do with the electrical system model to improve manufacturing, let's talk about what we can gain. So if you look back at the production ramp-up scenario I showed you earlier, we looked at how traditionally a ramp-up would be planned and how it can fall short as a result of challenges we encounter due to outdated approaches. So what could happen if we adopted a digitalized approach using the digital twin and digital thread? First, during the engineering design cycle, we expect first-time quality to improve as a result of utilizing standardized embedded information libraries and design rule checks and validation analysis. So naturally, we would expect to benefit from an improved design quality during ramp-up, and we would adjust our curve accordingly. But that's only part of the story. By leveraging digital twin in production, we can perform process simulation, analysis, optimization, and validation before we start manufacturing. Add in the digital transfer of information and increased automation, and we will severely reduce the number and severity of disruptions encountered during ramp-up. While we still may encounter unforeseen issues as we head to full rate production, we've reduced the severity of the issues and improved our responsiveness, which enables us to not only meet but exceed today's normal expectations for realizing full rate production. As I mentioned before, companies have realized benefits in adopting this approach in error reduction and time savings. So what does this mean overall? When you think about the landscape that's already shifting relative to electrical system design, there are some clear reasons to head down the path of digitalization in harness manufacturing. First of all, you can reduce overall program risk associated with production ramp-up. Second, achieve profitability by meeting customer expectations for affordable first-time quality. And third, realize increased productivity. And finally, keep in mind, staying a step ahead of your own challenges and shortcomings, your customer demands and pressures, and your competition. That concludes my presentation. Thank you very much for your time and attention today. At this point, I'm happy to take questions.
Hey, this is David. Thanks. Hey, I've got a couple for you.
Okay.
I was just thinking my first job in the business was building wiring harnesses for the auto companies, and that was a long time ago. And I'm just wondering if you're seeing any market penetration in automotive or anywhere else.
We are actually seeing the automotive market probably taking the lead in this area as compared to aerospace companies. Mm-hmm. Having an aerospace background, I fully appreciate how a lot of our companies have products that are actually in production for long production runs, not to mention their service lives. Mm-hmm. Whereas what we see in the auto industry certainly is, every year is a new model year. They're able to introduce features relatively quickly because they plan around that cycle. And so we've seen adoption of digital technology in the auto industry, really pretty firmly.
Yeah. Interesting. Yeah, I remember there was a cycle there. It was an annual cycle that we were really busy in the wintertime, then laid off everybody in the summer. I say we're busy in the summer, and then the fall, once we got everything working, then they kind of laid everybody else off. I also remember that the ground wire for the 1980s Fords was number 57, which is kind of scary, but I remember that. I spent a lot of time with that. So you showed the chart earlier on airplanes, and you showed the amount of wiring that is in airplanes is going on. And, and I saw, and I know the 787 is a lot more electrical, right? That they replaced a lot of electrical, hydraulic stuff with electrical on the 787. But then at the same point, a lot of the stuff is networked. They weren't really networking anything in the 737 world. So I'm just kind of curious where the increases and the decreases in wiring are coming from.
Well, so I don't know a lot about the 737 itself.
I'm just saying old airplanes.
Yeah.
Pick an old one, yeah.
Pick an old one. Well, I can tell you this. In my recent experience over the last 5-6 years, I was working in new product development on new aircraft. And we were seeing a trend to going more electronic. So what that meant is more communications networks within the aircraft, devices communicating within the self. I mean, this is beyond fly-by-wire. This is this is going to just the way the different components on the airplane communicate with each other. You get to beyond the glass cockpit, we were going to touch screen circuit breaker panels, in the overhead. So certainly a lot more electronics and a lot more digital communications throughout the aircraft. And so, that takes a lot of the mechanical elements out of airplanes, which, can be things that wear out and fail. Certainly that's true with electronics as well. But the benefit you get from that is certainly the more digital components you have, ability to upgrade without changing the mechanical parts. That opens the door for that. So yes, but certainly you can see if you look back at that chart, the 787 was a huge leap ahead in electrical content, and I'm not aware of any other models yet going quite that far, but we are definitely seeing that trend.
Interesting. I was also looking at your old wire boards, the drawings, the descriptions you have of the wire boards. They're kind of static, right? Are you seeing in wiring development or communications with something kind of more dynamic, something programmable, or a wire board's pretty much what they used to be, a bunch of nails, tied into a hunk of?
It's the what's becoming available out there is really pretty impressive. Certainly, there's the what I showed here, where you can lay out a form board, with the thought that you would, print that out and lay it actually on a physical board with physical clamps. There are devices out there that are being made now where they effectively, I'm not exactly sure what the technology is, but effectively it reminds me of if I had a LED television, flat screen, right, that would display the form board content with relocatable fixtures for the wiring that could be, turned on and set up, and you lay up a harness and you build the harness on it, and then when you're done, you put a different overlay on it, reposition all your fixtures and do a different configuration. Those components are out there, and again, if you're, the nice thing is if you're doing this stuff, in a digital format as well, it becomes easier to feed that information, into a print or into some technology like that where you can display it. We've also seen, I've seen companies investigating and experimenting with the use of like the Google Glass type technology. Where they're actually wearing glasses, and the camera on the glass can recognize components, or maybe your manufacturing paperwork. It can scan it, and if you're looking at a connector, just by looking at it, it will bring up the layout of that connector and all the pins and wire connections to that connector, which is, I think, pretty cool.
Yeah, that's interesting. You showed connections between the wiring harness and to the test equipment, right? Test systems that we're checking it, right? And that was kind of part of the digital twin concept, right? That there's integration between the design and the schematic, and then the testing process and everything. Is that communication to the, I guess we'll call it ATE or automated test equipment? Is that something that's managed by your software and tools, or what's that communication look like?
So we are working in that direction.
Mm-hmm.
So right now our tool suite, it continues to expand as industry needs it and is ready for it, and I think we're staying ahead. So we are, what I talked about today was primarily in the electrical distribution system design, which would include the traditional power distribution and whatnot, harness design as well as documentation. But we are also developing and have tools developed in network design, software design, even going into embedded software into discrete components, and that enables what you're talking about, which is simulations. Siemens actually has a good set of simulation software. I'm sure there's a number of other companies out there that do that. So kind of pulling on what you were talking about earlier with going digital and having the digital twin and digital thread, it really enables the use of analytical tools and simulation to validate a product before it's built. Once you're cutting metal or doing wiring, your cost of change, it really goes up quickly.
Yeah. Yeah, the automated validation is something that we're certainly looking at, right? You should be validating, and then there's another term that's out there, which is
right.
Commissioning, virtual commissioning.
And maybe one thing I didn't describe in much detail here is in our engineering design tools, we have the ability to add constraints and rules to do a lot of design checks for you. Find unterminated wiring, things that are not connected properly or misconnected. We can trace signals through 3D space to make sure that you don't have power wires running too close to flight control wires or fuel tank indication systems.
Yeah. Yeah, that's cool. So we're kind of don't have any additional questions for you. What do you wish we'd asked you? What else would you like to say?
Let me see here.
That's one of those questions that feels like a softball. It's actually kind of a hard one. Sometimes questions feel like they're hard questions or easy ones. But.
Well, what's interesting, and I've talked to other groups sort of about this content, and I heard the question you answered earlier, and what was what's the hardest part about doing this, right?
Not the vote question.
It wasn't the vote question. It was what is the hardest part about this transformation?
Yeah.
And I think I would echo exactly what you said. I've experienced this in my own engineering teams, and that is the cultural changes that have to happen within a company. Whether you're talking about changes in the way you do the mechanical work or the electrical work, I've seen that, it may have to start in the engineering world, in the design world, but carrying that through the entire business can be a bit of a change for everyone. And it's in ways you don't expect. So the important thing to realize is that, companies that have done it and are doing it are seeing great benefit from it. So, it's tough to get through, but, it's been shown the benefits are real. So that, I think, is a point of encouragement for people to make a start if they haven't.
We've come a long way. The technology is there, but then culturally, it's kind of hard to get there. So.
Yep.
Yeah. Well, I guess, we're kind of we're a little bit early, but I think we're about done. I'd, Steve, particularly like to, thank you for attending and presenting at this. It's just really interesting to see how, we're all kind of working the same direction together, which is really, really pretty cool, and just trying to think more broad-based, which is, you know, really, really challenging and really, really beneficial all at the same time. It's just an interesting mix. And you know, I remember when the ISO 13399 people started showing up to STEP AP 238 meetings, which since you guys were all paying attention, you know what that means. I said, what are these guys doing here? Who cares about the cutters? That doesn't really matter. And then really, really thinking about it, you know, and realizing we're all kind of in this together. We've all got to work together on this. And so really appreciate your willingness to present and spend time with us here today.
Well, I greatly appreciate the opportunity, and I hope that those listening got something out of this and maybe helps show them, you know, their next steps and gaining some benefit. Yep.
Our next summer is the same. Our next seminar is on Thursday, same bat time, same bat channel, and we thank you for supporting and attending GPDIS this virtual session, and we will see you all in a couple days, hopefully.